I do not have the screen in front of mine, so that I should occasionally look behind me what I am talking about, but thank you very much again for coming, and I will immediately move to my lecture. One thing which I would like also to point out, I'm so sorry that I do not speak Russian language. I'm here for 2 years, and originally I am, as you will see, from Serbia, but I came from Britain, where I used to spend more than 15 years. And I'm very happy to be for the second time in Irkutsk. When I talk to my friends, I say that I'm now in the time zone of Beijing, what is only telling how large Russian Federation is. But then I say more 4,000 kilometers to Vladivostok. So that's sometimes incomprehensible how large Russian Federation is, which is considered as 1/7 of the planet. Well, USSR was 1/6 of the whole planet. Anyway, I'm very proud to be here, to be in Russian Federation, in which has so many scientists, so many artists, so many achievements of the civilization. And in this context, let me start my presentation. I don't know all your background. You might be from mathematicians background, but I'm an engineer. Today I'll really give a lecture which will be having this engineering flavor, engineering background, but where I'd like to point out the importance of implementation of complex science, top mathematics, applied mathematics in solving some of problems which are of huge importance for energy sector, and we are, I think, recognizing the importance of energy sector today and always, and also for future. Very quickly about my biography. I started my career at the University of Belgrade, where I achieved in Serbia, where Yugoslavia at that time, where I got all my degrees. Then I spent some time in Germany at Technical University of Kaiserslautern, then in Saarbrücken as a Humboldt Fellow. An important part of my career was part of career where I worked for industry. ABB is a top company, international player, producing automation products and power energy products. For example, big transformers, big generators, and so on. Then I spent 15 years at the University of Manchester, and 2 years ago I joined Skoltech, Skolkovo Institute of Science Technology, and where I am here in Russia. And let me say a few words about my other activities. Already mentioned, I am editor-in-chief of International Journal of Electrical Power and Energy Systems, and I look forward receiving also your papers. At the same time, I'm so happy that this presentation will be converted into for your journal. It's my big pleasure to write it. It will be in English, but interestingly, my very first publication, international publication, was in Russian, in Electrичество. I'm so proud. It was about устойчивость, stability of something. I was so happy. So that's quite interesting curiosity. My first publication ever published, international publication, was in Electrичество. Not because of my Russian, because the third co-author could speak Russian and wrote it in Russian, and so it's a very nice experience. I worked also in a number of international bodies. The important thing is that I'm not only listed, I'm trying to give my personal contribution in IEEE level and also SIGRE level. And my further activities are related particularly to my connections and collaboration with Chinese academic institutions, so that I remember that I met also colleague Suslov and other colleagues in Shandong University when we met in Jinan, and I work also with Tsinghua University, Peking University, so in general terms in China. It resulted as a result of many Chinese students in United Kingdom at the University of Manchester. And I'm, of course, linked to Belgrade as a visiting professor. I collaborate also with Danish Technical University as Otto Monstedt professor, and naturally I collaborate with other universities from United States and the rest of the world. Collaboration with Russian academic institutions is natural, so that I'm very happy to collaborate also with universities from Irkutsk, and in my strategy I'm planning also to talk to colleagues from St. Petersburg and other institutes where electrical power energy systems is part of research. And if I now move forward with my lecture, the presentation content is as follows. I'd like to talk in general terms about electricity generation and production, a couple of statistical information. I'd like to talk about future energy systems, about smart technology. Today, if you buy a mobile phone, and it must be smartphone, everything is smart. So suddenly we have also smart grid, smart energy, everything is smart. But, well, it's not too bad, because when you talk to politicians and say smart grid, oh yes, smart, they are waking up, and then they say, okay, let's invest money into this. If it is not smart, we worked always, when it comes to energy sector, it had to be smart. And I'd like also to say a few words about data science and digital twin aspects and some practical results from my previous work, because I used to work with industry, with British industry, and also with European industrial partners as a part of European projects. Few statistical words about importance of energy sector. This is electricity generation. What happened? I was invited by people who are non-specialists for engineering and to prepare a presentation. Then I really prepared very basic things, and I realized some very interesting information which I was maybe not aware about. That's why I have these basic slides. This is information about electricity generation historically since 1985. Okay, since 1985, let me see, maybe this position is better. And you can see the energy production in China. Politically, China was not that developed at that time, and then full industrialization started in 1990, and lots of manufacturers moved from the Western world to China. Suddenly, you need energy to move, you know, motors and so on, and as you see, massive increase of electricity generation in China. It is 8,000 terawatt hours, what means we are talking about huge numbers. Suddenly, somehow, I didn't put Russian in this scheme, but I have in the next slide. You see, USA more or less similar, India increased, and you can see where the production is happening. That means it is India, China. This trend is very important to understand it. On the other hand, when it comes to Russian Federation, let's see what is now electricity production by source. Coal, standard. Gas, almost standard. Oil, as you see, and nuclear is slightly, I can see, increased, and water, what is so important that you have so much water. Water is so fantastic because it is almost clean energy, and hydropower plants are a fantastic thing. But look at the importance of the gas, and that's why all researchers working on gas, geoscience are very important. Just discussed about it. On the other hand, let's look at the share of primary energy from low carbon sources. When it comes to low carbon source, we talk about renewables like sun or wind, but also nuclear. Nuclear is defined as a low carbon source. Yes, all right, so you can see increase in China, USA, United Kingdom, from Russian Federation as well. We see also the increase of all these low carbon sources, but including nuclear. But now let's see, excluding nuclear. Without nuclear, you can see that in Denmark you have incredible increase of only renewable energy sources. I am now talking about hydropower, solar, wind, geothermal, bioenergy, wave, and TDL. You know, translator will translate all these points. Denmark, so many wind farms. And Denmark is a small country. It doesn't mean that they are producing billions of energy. No, they're just a small country. And then if it is 35% per country, you see increase in Germany, in China. But Russia is more or less not huge changes. The question is, why don't we have so many wind farms in Russia? The question is this energy more expensive or less expensive? I'll tell you. Renewable energy coming from renewables is more expensive in Russia than energy which does exist, because you already have sources. You're lucky, you're happy. On the other hand, you have countries in which you don't have energy sources. That's why energy coming from renewables is cheaper. Then they are very happy to push this to agenda. That's logical, and this is acceptable. But this is just reality. It does not mean that Russian scientists should not be involved in development of renewable energy sources, technologies, because this technology can be exported. I'm informed that you have top, for example, solar-related facilities. So, also, about energy transition in Russia. Skoltek was involved in, together with School of Economics, in preparing a document to advise also Russian Federation and government about future trends. But at least according to First Deputy Prime Minister Andrei Belousov, the following areas are of huge importance from Russian Federation: energy efficiency, renewables, decentralization and distributed energy sources, digitalization, including hydrogen and decarbonization. We also have huge cities in Russia. Moscow is a massive, huge city, St. Petersburg. Irkutsk belongs also to big cities. These cities should be clean cities with clean air. Burning coal is creating pollution. We are aware about that, particularly in China. It's very complicated problem which has been recognized. It was recognized almost 10 years ago or 15 years ago, and China has already done a lot to make their environment cleaner. You can be very rich, but if your air is not good, then you have really a big problem. Anyway, my research and work is on making society better through generation of sustainable energy, through generation of clean energy, and of course having a secure, reliable electrical power system, optimally planned, what means with the reduced costs and with maximal utilization of technology for having efficient electrical power system. So we are coming to smart grid, which is based on technology and smart solutions. It is information about Britain. Just one slide from one day. It was almost a day before my presentation, which I gave in Moscow. Maybe there is a date here, but maybe not. I want to point out that 51.2 renewable energy was produced. That was, I think, night time in Britain. So just as one interesting example. Something about future energy systems. The fact is that we have a tradition. What is my work about? I'm an engineer. I'm not a top scientist, mathematician, and something like that. I am an engineer, but the role of engineers is to make one technical system operating reliably and safely and in a secure way. That's not easy. And I'd like to point out that electrical power system is the highest achievement of mankind. That's a system operating in real time. You cannot store energy in the way like we are storing terabytes of data. The system must operate in real time. Produced energy must be consumed at this very moment. We have some storage technology which is helping, but this is the biggest achievement of humanity. So traditional approaches, we have generators, we transmit energy and then send to customers. And the flow of energy was unidirectional, what means from generator to customers. Now we have also renewable energy sources like wind, like solar. We have also electrical vehicles and the need for changes in cities, having electrical cars. And there is a game-changing technology which is storage. Russian Federation is very important in this context because for storage we need lithium, but there is also a redox flow technology and Russia is also very strong in this. Because I talked about storage of energy, energy must be used in real time, otherwise system can be unstable. Frequency must be always 50 Hertz. And if we can quickly store lots of quantities about energy, because you could see I'm talking about terawatt hours. And we have to consider huge facilities which we need when it comes also to storage. And what we want to achieve? We want to achieve that the level of produced CO2 is neutralized somehow. And in this context, Russia is very lucky. You have huge forests. These forests are contributing to these carbon neutralizations. We cannot talk about this type of carbon neutralizations in countries which are purely deserts. There is no vegetation. So many aspects. And if we talk about introduction of renewable energy sources like wind farms, storage, solar, there is one new technological challenge. Let me describe that as a challenge or problem. Traditionally, electrical power system was operating in such a way that generators were connected, were synchronously connected. What means we talk about the alternating current, AC system, 50 Hertz. Nikola Tesla. I was born in a place which is 70 kilometers far away from the place where Nikola Tesla was born. Quite interesting statistics. And generators are connected directly, synchronously. But how can you connect a solar panel? Because output from solar panel is DC current, not AC, not 50 Hertz, it is DC, like battery which you have. Similarly, storage. And also some types of wind farms, it is so-called type 4 wind farms. They are connected over power electronics. This is causing the fact that generation is not connected synchronously like Tesla has designed the system. It's now connecting asynchronously, and this is causing technical problems for operation of electrical power systems from the perspective of power system dynamics. Now we are coming to dynamics, to some basic features of the system. You know, every rotating mass is having its moment of inertia. That means a lot of kinetic energy. That is good in AC systems. But if you connect generators in which these rotating masses, suddenly this massive kinetic energy is reduced, and system is becoming unstable from frequency stability perspective. It's now a very specific topic. I cannot go deep into the topic, but I'd like to point out that frequency stability is becoming a complex problem. We can easily and quickly come into frequency collapse and the system blackout. That's very dangerous. So we introduce renewable energy sources which are asynchronously connected, but they create a potential problem of frequency instability. System is over, system is in blackout, everything is black, no electricity, because generators are disconnected and so on. On the other hand, there is one phenomenon in the system which is related to voltage stability. We like to have voltage which is 100% across the whole system. But it is related to short circuit aspects. And short circuit means a huge short circuit power, short circuit current. In systems in which we have lots of renewables, this short circuit current is small, but it is reflected in the problem stability. And again, voltage stability was the cause of many power system blackouts. For example, big power system blackout in Italy in 2003, something like that. The whole Italy was black in one summer night, what means it was a total blackout in Italy. I pointed out that the integration of renewables is now having a consequence that the system is becoming more unstable, so that we must do something against that. Historically, let me just give a little bit history of some power system blackouts. We had a number of power system blackouts, but normally system is operating in normal state, and the system can be affected by disturbance. It can be a short circuit on a transmission line, disconnection of transmission line, and then what can happen, slowly we can lose elements in the system, transformer or cable, but this is a process which can last 10 hours, for example. We slowly lose elements, but we are using different measures to retain the system stability. But if unexpected event happens, which we didn't plan, for example, wrong operation of power system protection device, suddenly we can have a so-called fast cascading events, very quick disconnection of large number of elements of power system, and this is leading us to blackout. Blackout means generators disconnected, load disconnected, transmission network is not operating, and the system is not existing. And this is now the problem. You see, this is the number of disconnected elements in the system. Is in a very short period is disconnected. This is something according to Italy blackout in September 2003. And you see, with integration of renewable energy sources, chances for this kind of blackouts are much more higher. And we want to have real-time system which can prevent this kind of events. And let me discuss how can we do that. So a little bit about also impact of severe weather conditions. This is a blackout which happened in Texas in 2021, just as one of examples. Let me add one more interesting challenge which is happening today. We are integrating different energy systems. We call them also energy vectors. We have electricity network, but we have also gas. We have what else we have? We have heat network, we have transportation, we have also ICT network, and we are integrating them together to operate together. By this, we achieve savings. We create a more flexible network. Flexibility means that by integrating heat and electricity network, we can optimally utilize renewable energy sources. And it is now a separate topic about utilization of different methods of optimization techniques, solving very complex nonlinear stochastic optimization problems. Lots of space for top mathematicians. But how are we integrating these networks? We have so-called coupling technologies which naturally exist. Very simple example. Electricity network and gas network. You have a gas station with gas turbines, combined cycle gas turbines, CCGT, combined cycle gas turbines. What means? Gas is necessary to feed a generator so that these systems are coupled in this way. So gas network is providing gas to the generator operating using as primary energy obtained from gas. Or we have house appliances in your kitchen. You have heater based on gas. So it's also connection between heat, gas, electricity, or we have heat pumps also. So in this way, different energy systems or vectors are connected to each other. And if we assess operation of the whole system together, it becomes suddenly an interesting opportunity to minimize costs of operating of such a complex system. By minimizing costs by 1 promille, we reach huge savings because it's very expensive system. We also talk about smart cities. Interestingly, in this graph, everything is smart. Whatever you see, smart manufacturing, smart government. What is smart government? I don't know who made this slide, but smart government, and so on. So we could, but what I would like to say for this slide, we use also communication network. Communication network means that all different systems like transportation or buildings or manufacturing are connected to each other. This is now leading us to the concept of Internet of Things, where everything is connected to each other. But you have processes where this concept of Internet of Things is good as such, necessary, but I do not say it must operate well, properly, reliably, and you cannot allow a system falling down like blackout, like in ICT system. You know, you have your laptop or computer, it is being collapsing, not operating, but in 1 hour it works with relatively small consequences. But with a big electrical power system, we cannot do that. So, key aspects of electrical power system is monitoring, control, and protection. Monitoring means let us see what is the state in which the system is. It's a dynamic system. We have to assess where the operating point of the system is. If we, for example, view security of the system, in which point from security of the system perspective we are, where are security limits? They are changed in real time. That's again a space for complex science, for research, for work. Control, you know, it's a dynamic system, like aeroplane. It has its dynamics. Generator is a dynamic component. Transformer is steady state. Transmission line is steady state. Of course, we have also transient processes, for example, during faults in the system. They are expressed through differential equations, so then we also use differential equations. It's a kind of dynamics, but it's a dynamic system with its control. We are controlling frequency, we are controlling voltage, we control temperature, but the key control loops are voltage control and frequency control. And we have different types of, for example, frequency control. Primary control, 10 seconds. Secondary control, 10 minutes. Tertiary control, which is economic aspects, it's going to maybe a couple of hours. So we must understand the physical process to understand its dynamics and to see how we will control the system. Integration of renewables is affecting dynamics, is making control process more problematic. That's why here we are. We have to help the system to integrate renewable energy sources, as it is happening in a number of countries in the world, maybe in Russia, not at the level because you're such a huge system, huge country in which you already have enough energy, and it's not such a business case to integrate renewables because you already have energy. So I'm just pointing that out, but I'm also pointing out that it is still important that Russia is existing on the market, providing solutions and being ambitious to help. You are at the market, like in the cheese industry, like in the food industry. And protection, these are processes which cannot be controlled. For example, you have a short circuit, you must disconnect transmission line which is affected by the fault. Power system protection is so important because I wanted to say, just to give information, that how information is obtained in the system. It's now very engineering and not easy to talk to those who are not without engineering background in a limited time. So this is here one point in the system. For example, 22 kilovolt substation, power substation. We have connection of so-called switch gear in which we have circuit breaker, disconnector, we have cable connection. We can have different realization of this. That what you see on this single line diagram is actually in distribution level, for example, 22 kilovolt. This is, and it is not easy to translate, SF6, sulfur hexafluoride substation, which is looking as follows. It is, I used to work in ABB exactly on this. And I used to work on development of digital devices controlling such a system in which we have many elements. Look, it's not easy even to talk, to discuss. I needed 2 years to understand how everything works and became then a specialist for power system protection and operation of such medium voltage switchgear elements. But information is obtained using sensors like voltage transformer, instrument transformer, and current instrument transformer. So we are measuring voltages and currents. How? Here it is, a bit more complex. Not easy to translate, to translator, but this is a substation, 22 kilovolt, and now we have circuit breaker, disconnector, and finally we connect the motor. Motor is, for example, for water supply. We need the motor pumps. But we have current instrument transformers and voltage instrument transformers. And this is now digital unit. Voltages and currents are converted from analog to digital form. And we are now in a digital device. So we got information from the system, but this is not the only information about the voltage and current. We also want to know what is frequency, what is temperature, what else, many things. So we get data, and we do not have only one substation. We have many substations and lots of data, so we move to a big data case. We have on a daily basis many gigabytes which have to be stored, processed, transferred. Knowledge should be extracted from it. We should understand securities of the system, reliability of the system. So, as you see, I'm talking about a system which is geographically huge, important, and with lots of opportunities for data science and implementation of top technology. Well, we have data. These are now different configurations like busbar A and B. They are connected, different configuration. And what is also important, we have digital devices which are connected using ICT, information communication technology. They are connected using, for example, fiber optics communication channels in which we use different communication protocols. again, lots of engineering things. Communication protocol is like a language, so we are now using communication protocol, a little bit Russian, a little bit English, but we understand each other. The same is with devices. They use different languages, like IEC 61850, or LON communication protocol, Modbus, SPA, Profibus. Why do we have so many different communication protocols? Because of industries. Because company ABB used SPA protocol. Profibus, Siemens company. LON is coming from car industry. Modbus, very simple communication protocol and so on. As you see, single engineer working with this must really have lots of knowledge to understand the system, technology, ICT, and so on. So today, a modern engineer must be able, must have a multidisciplinary approach to that what the engineer is doing to cope with so many questions. And finally, an important point, just making a summary, we have substation. This is that what you see sometimes when you drive car and you see in fields. These are these substations. This is big transformer, circuit breaker, switchgear. Then we have communication infrastructure. These are fiber optics. Coming to relay room, we have protective devices. And we can move to control room and to the grid control room. So grid control is a room. So this is, for example, Rossetti here, Rossetti. And this is system operator, which is controlling the operation of the whole system. So information, this is data flow from bottom to the top. It is a vertical data transfer. And here we have actually horizontal data transfer, horizontally between devices. So, and now I would like to mention something about one of technologies which can help and support operation of modern electrical power system. It is based on so-called phasor measurement units, and it is wide area monitoring, protection, and control. This is one paper published in 2011 with a very nice group of researchers and engineers, professors, all of them almost. But I'm very happy that 3 of my PhD degree students were co-authors. Gustavo Valverde from Costa Rica, Deju Tsai from China, and Pavel Regulski from Wrocław University from Poland. And the rest are famous people in the area. So it's about the following. We have traditional devices for protection and control and monitoring. They're part of classical technology used in electrical power systems. And if we synchronize operation of these devices in the context of time synchronization. Time synchronization means, we have now watches, but we don't have the same time in our watches. But if we receive a signal in which we synchronize all of our watches, suddenly we have watches with the same time. For us, plus minus 1 minute, sometimes 15 minutes, academic 15 minutes is okay, but for these, microseconds synchronization is important. 10 to the minus 6 microseconds. Devices must be synchronized to microseconds. And how to do this synchronization? We can use different synchronizing technologies. GLONASS, satellite technology. Also GPS, Galileo, Baidu in China. So this satellite infrastructure can help us in synchronizing operation of these devices. This synchronization is important, something what is called of angle, of phasors, of voltage phasors, something like that. I'll not go into these details, I don't have time, but this time synchronization is helping us because, as you see, we can have different, these devices located at different locations. If we integrate them together, for example, from Irkutsk over Novosibirsk, then St. Petersburg, Moscow, then south in Sochi, we can integrate all of them, and suddenly we have a system which can make state of the system much more easier than before. without synchronization, the problem is non-linear, complex iterative solution with chances to diverge. With time synchronization, the problem becomes linear. Non-linear problem needed 10 minutes, 5 minutes, 2 minutes to be solved. Linear, 100 milliseconds. So we totally make a paradigm change of paradigm, how to operate the system from just the monitoring what is happening in the system perspective. So that's now technologically how to do that. Now what we need more, we have phasor measurement units, what means that these devices with time synchronization, they are now called phasor measurement units. And we obtain data from the whole, geographically whole Russian Federation, but it can be also Russia, China, Mongolia, continental part of the Europe, what is the case, so that we have a wide area monitoring system. And to do that, we also need communication infrastructure, which can be different. Technologically, power lines, modem, phone lines, or local area network, or microwave, or fiber optics. Now we are in ICT world, in the world also of cybersecurity. In 2016, independent on reality today, there was a cyber attack in Ukraine, and they experienced blackout because of cyber attack. It's nice to have it, but it must be cyber secure. So engineers responsible for protection of having secure systems from data perspective are then also policy, which data are private data. Each company, maybe it's a very private information about frequency in parts of the system, so it's a policy and regulation. So many aspects which have to be seriously considered. In this context, I already mentioned we have lots of data. No data, problem. Too many data, again a problem. So, we are moving to data science and options for digital twin aspect. Big data, I'll not now mention all aspects related to big data, but I want to point out that the volume of data is significantly increased. We have more and more digital sensors. We have very capable ICT structure, which can transmit lots of data across the system. And having such a system can help us to have more secure power delivery in the system. I'm simplifying that a little bit. The question is how to optimize such a huge system, and who should be involved in this process of optimization of such a huge system. And in this context, artificial intelligence can be used like in all technical systems. I will not elaborate that too much, but I'd like to point out that today machine learning based approaches, what means usage of statistical tools to explore and analyze data, they help us to extract information which is needed for operation of the system. Now it's a very broad statement. And I'll give some examples. For example, we want to monitor what is the level of kinetic energy in the system. This can be done by using classical approaches. But if we create a system based on machine learning, for example, graph neural networks, which you have to properly train and to implement, suddenly we will have a system which can quickly monitor system kinetic energy, actually power system inertia, which is actually inertia. We want to know what is the level of inertia for frequency control, for example. And also we can move to deep learning approaches in which we use multi-neural network architectures. We are right now working on algorithms at Skoltech jointly with Belgrade and China on algorithms for monitoring power system strength or fourth level. So when it comes to data, it's about aspects related to analysis, to structure, different algorithms, different processes in which we have involvement of programming and solving problems and knowledge extracted. So this is a very brief overview of my research activities with my researchers, which are capable data scientists, to solve some of monitoring, control, and protection problems of electrical power systems. And a digital twin is just one of options in which we have a physical process. For us, it's not a train, it's not a, I don't know, building. It is a wind farm, for example, with a very sophisticated model of the physical process. This model should be based on the application in question. It must not ultimately be high fidelity, high quality model. It should be that what we are assessing. Sometimes people say it must be high fidelity, the best possible model, having everything. But as an engineer, the model of the physical process should be based on the technical question which we are solving. Anyway, this is a replica, it's a model of physical process. And we have synchronization between the process and the model. What means that the model in real time is always that what is a physical process. That's okay. But at the same time, we receive data from the process, data from the model, and we have now real-time data plus historical data. By combining them together, plus by using artificial intelligence, create a very interesting digital twin of the whole process in which we are achieving the following, that in real time we can make sure that operation of this physical process, in this case it is a wind farm, is optimal. What means we consider security, we consider reliability, optimal integration of wind farms to the rest of the system, and so on. Instead of this wind farm, which is now presented, we can have also part of distribution network, part of the transmission network, or integration of distribution plus a transmission network. This is my collaboration with Shandong University with Professor Horan Zhao and Professor Ding Lei. Particularly Horan is involved in this, and we have a very nice example of real-time application of the system. Let me double check timing. Okay. Some practical examples very briefly. This is a project called Visor, in which we used phasor measurement units integrated into the existing SCADA system, supervisory control and data acquisition, in Great Britain. It was a demonstration project with company GE, with National Grid, Scottish Power companies. We worked on monitoring aspects, but we also wanted to expand the whole process, not only on monitoring of something, but also on controlling and even protection. Very big project, 3 years. And the result was connection of phasor measurement units in the whole island, I mean in the whole Great Britain, and real-time operation of the system. So you have now lots of data, I mean lots of sensors of different type. I'm a little bit now talking faster because of timing. The point is, this is now phasor measurement units, time synchronized using GPS. Also, we proved that you can use in parallel GPS and the Galileo system of satellites for one application, what is very good. So I believe that also GLONASS and GPS can operate in parallel. So as engineers, we do not care about politics and ownership. We just prove they can operate together and support each other. If you have a contract, GPS and GLONASS, they work together. Nice. And the important aspect is that the whole system was tested at the University of Manchester using hardware-in-the-loop laboratory facilities based on a real-time digital simulator, which is really very modern test facility. And we, for example, worked on modern power system state estimation, in which we used not only traditional data obtained from conventional measurements, but also phasor measurement units based data, and creating a hybrid state estimator or state estimator only based on phasor measurement units, which is a linear system, and then the problem is solved in real time. And I will demonstrate that through collaboration with Technical University of Delft, Professor Popov. He's about to become full professor in 1 week, what's very good. And my former postdoctoral researcher, Dragan Cetenovic, he's originally from Belgrade. He's now at the University of Manchester. So we used a real-time digital simulator to simulate a medium voltage network. And in real time, we transferred data from the system to the state estimator, in which we estimated the system state. And it's like in a real electrical power system. Again, very quickly, that is a real-time digital simulator, simulation of the operation of the system. So you see this is substation 1, substation 2, this is transmission line. We have voltage here, voltage here, voltage here. We have current flowing from this point to this point. Actually, we have active and reactive power flowing through the system. So that's the electrical power system, medium voltage network. And we have a limited number of phasor measurement units, but sufficient number to have a linear problem. And we use strategies of distribution network state estimators, and we estimate the state in real time. I talked that if we don't use PMUs, then we need 2 minutes to solve the problem. Now we solve it in real time, almost with the time delay of 1 second. So I will show that. Let me see, I have now to, let me see if I do this. No, I have to press, because it is a video, but I have to just touch the screen. Where is the, can it go here? Let me see. Let us go outside. Go to the previous slide. Go escape. Please just press this escape. Okay. If you can, it's like a film. Is it a film? Yes. Please press. Please. This. Just press this. You can press this. Just press. Press this. This. Yes. It's moving. Yes, it is moving. It's real time. What is now showed, you see, nothing is happening now. We will have a fault in the system. Fault, you see, we have measured and estimated. It's almost the same. Monitoring voltage in one of points. Again, fault in a real-time digital simulator. You have very close to each other, and I'm demonstrating that just visually we can see that what is estimated based on limited number of measurements, we can monitor the process. It is just a demonstration of capabilities. We are demonstrating that it can be done almost in real time with a time delay of only 1 second. But if we want to make it even better, this time delay can be 200 milliseconds. You see, 200 milliseconds compared to 2 minutes of the state. And this is a very good demonstration. We can move back to the normal presentation. Yes, thanks for this. And based on good monitoring, we can then also improve some of the stability activities like frequency stability. I already mentioned that the whole system is reducing inertia by integration of renewables, but if we monitor the system operation using phasor measurement units, we can create a system in which we will somehow create so-called virtual inertia in the system. It can be done by using wind farms, also solar energy and storage, and partially combined cycle gas turbines. That was a big 4-year project led by National Grid from Britain, in which I was leading University of Manchester plus Strathclyde University from Glasgow. And we worked together to make sure that after a big disturbance in a system, for example, a sudden disconnection of big generator, it is like having a car in which one of cylinders is suddenly stopping operating, one motor stops, and then the car cannot retain the speed of 50 kilometers per hour. But somehow we have a system which is based actually on some dynamics. I was very pleased to publish this paper. I'm always with somebody together, but at that time I was with ABB, and I published something what was very intuitively obvious by using so-called swing equation describing dynamics of a generator, and a couple of equations based on which, what's the technology? We measure frequency, and we measure rate of frequency change, and we know system inertia, and by this we understand what is imbalance of active power in the system. That's quite a long story. It's a presentation for itself. And based on this equation, we created the whole system, which was also tested at the Great Britain level, so that test was using RTDS, real-time digital simulator. These are these devices from GE company based on the formula which I showed, and that was testing facilities in which I will just show you for a test. This is now an equivalent model of Great Britain system, in which we made a sudden disturbance in one part of the system. It was a sudden connection of a big load, 1 gigawatt load, and the system responds with this new approach and without. So, without approach, we had frequency which dropped below 49.5 hertz, what is so-called statutory limit. That was bad, that was not good. With our approach, we made sure that the system frequency is far above this limit, and we contributed to system stability. This is just one of small examples out of many examples, and this test was one out of thousands of tests which we did, and now this new approach, it is called Enhanced Frequency Control Capability, very complicated EFCC. It is smart frequency control. It is now implemented in Britain. It's pioneering study, but it should be applied in near future. So let me conclude this presentation. Firstly, I had very interesting other examples related to prevention of power system blackouts, related to monitoring of demand or load. But in this presentation, my intention was that I demonstrate that electrical power system is exceptionally complex. There is lots of space for complex science, for graph theory, for artificial intelligence, machine learning, for application of nonlinear control. I recently also worked on application of, actually it's a method for detecting voltage instability based on maximum Lyapunov exponent. So to translate maximum Lyapunov exponent approach, it's very interesting. And here you are, young scientists, to help us engineers to have a more reliable electrical power system. in which we want to integrate renewable energy sources, but also to operate existing electrical power system in a secure and reliable way, where we are using modern technology. You could also see satellite-based, time-synchronized technology to support optimal operation of the system, also using data science approaches, fast communication infrastructure, cyber secure, and I'm almost sure that all of you will provide your own contribution. With these words, I can express my thanks to you. Thank you very much for your attention, and I hope that this presentation was useful. Thank you.
Thank you very much. Большое спасибо. Very interesting talk, I think, covered many different aspects of and various applications. So we have the panel participants from different countries, I think mostly from China, but maybe not only. So we have about 50 plus online participants, and so let me briefly introduce our panel discussion collaborators. One of them is actually professor and the Vice Dean of the College of Electrical and Information Engineering of Hunan University, the Director of Engineering Research Center of the Transmission and Distribution Energy, which is supported by the Ministry of Science of China, Professor Yun Li. Also, we have the professor of the Hohai University. Hohai is a sea and river. It's a of water resources university. Water is very important for the generation of the electricity, as all of us understand. This is Nankin, one of the largest cities in China. It's a Professor Yunhui Sun. Also, we have the speaker, the participant from Qinzhou University, Jifan Yan, which was kindly introduced by Professor Tercia to myself. Also, we have our long-time collaboration professor from the Information and Electrical Engineering faculty of the China Agricultural University from the capital of China, from Beijing, the Professor Jishan Yang. And so also we have our local participants, also the Professor Nikita Tomin, the head of Laboratory of Energy System Institute of Russian Academy of Science, Professor Denis Fedosov, also from our universities. He's the head of the chair of the electrical systems, networks and systems, stations, yes. Yeah, also online maybe we have the Professor Natalia Eisenberg from the Department of Electrical Systems, the PhD in economics. Economics is also very important for this is a system science as electrical engineering. So also we have the head of Laboratory of Reliability, Professor Krupinov. Dmitry, for reliability is very important, so because it's a critical infrastructure, energy. So I hope I didn't. Okay, and also we have our very good engineer Alexander Domyshev from the electrical engineering, also from Russian Academy of Science, and also professor of our university. So now we have time for the discussion, and also all of the panel speakers have now a chance to ask questions and also say something in relation to this presentation. So maybe we can start with our online, and then we will switch to. Also, I forgot about the head of the department. Sorry, you're just hidden under. So yeah. Okay, maybe you will later say something also. Yeah, sure. So maybe we can switch on to the mode for online speakers, and maybe we can give the words to our Chinese friends to say something, because now the most advanced power network, I think, located in China, if I'm not wrong. Yeah, so China is doing very well. started under the supervision, I think, of former Soviet Union, and they are very good. Yeah, say, please say something.
When it comes to modern electrical power system, we are also talking about high voltage DC connections. In China, they have parts of the network which are high voltage DC, but they still have AC, but 1000 kilovolt. So in continental part of Europe it is 400 kilovolt, maybe in Russia it's 700 as well. In China they went and decided to go to 1000 kilovolt, what is 1 million volt. But they also have meshed so-called voltage source controller based HVDC network, and that's also something demonstrated in real time. One of problems in this kind of networks is DC circuit breaker. You know, AC current can be easier interrupted by classical interrupters by waiting for zero crossing. Then we disconnect, there is a little bit arc, and that's fine. But how to interrupt DC current? Because if you want to interrupt current from one current level to zero, we have a huge rate of current change. What is followed with a massive voltage? That's problem. We need zero crossing. And then circuit breaker should be big like this big room, for example. So that's power electronics, what they have to solve. In China, there is also this kind of development, but also in continental part of Europe, like companies Alstom, Schneider, Siemens, it's about ABB, also DC circuit breaker. So anyway, in China, they already demonstrated meshed voltage source converter based DC network.
Thank you very much. Yeah. So there is a big war between AC and DC in some way. Still, exactly, like Tesla and Edison. Yes. So, yeah. So, if online participants can switch on camera and maybe ask some questions, it will be really appreciated. So, if
can you hear me?
yes, I can hear you, but I cannot see you.
I'm Zhifang from China University. So
yeah.
First, thank you very much for this invitation to participate in this seminar, and thanks for Professor Vladimir for the great introduction. And also thank you for your continuous support for Chongqing University. And Professor Vladimir have hosted, I think, a dozen of seminars in Chongqing University, which really broaden our horizon. And here I have a very quick question for this speech. And I think Professor Vladimir have talked about the data science and data technology that may increase the flexibility and the optimality of the power system operation. And I know that in both Russia and China, we are the researchers from the academia and the industry have done a lot of work to utilize the data to improve our operation. But I think in China, there is a very big bottleneck is that I think there are two faults. And one is that the data in power system is highly, the power system operators, they really care about the data security because they are very confused if they want to share this data with the researchers and with maybe IT companies. And I don't know if this is the same case in Russia. And I want to hear your comments on the data security here. Okay.
Maybe there should be switch on. Oh, sorry. Yeah. Okay. Thank you very much. So there is this microphone and a tunnel effect. Yeah. Okay. The question was about I think data availability. Am I right? Security of data. Yeah. So please.
So greetings to Chongqing University. By the way, if you don't know, Chongqing is maybe the largest city in the world. Maybe Tokyo, Chongqing, 32 million people. I didn't know that. It's near Chengdu, where panda, a nice deer animal is. And I collaborate with Chongqing University. So the question is, thank you very much, Professor Yang, for this question. It has to do with ICT infrastructure and data. One of questions is, who should be the owner of this ICT infrastructure? Should it be the company like Rossetti or China South Grid, Southern Grid, or China State Grid? Who should be the owner? Or shall external company like Line, we talked yesterday, be the owner of this infrastructure? And if it is the case, in any case, it should be regulated, the policy. I also mentioned the importance of policy. Who is the owner of data? Data are sensitive. We cannot, for example, there is a blackout. And the question is, who is guilty? I'm very brutal. Who is guilty for this? And then, oh no, we don't want to give data. I was working when I was in industry, when I had this situation that I had to help solving a communication problem, and then I saw that the problem is between two companies involved, but then the question, I had to be very diplomatic not to say anything loudly, because the intention was that companies share the costs 50-50, because, so you see that sensitive data can be very sensitive. On the other hand, data must be protected and properly protocolized. That's why these measures related to data security, and that is also very, very important. Data storage as well. Think that companies from electrical power system would not be happy to use TCP/IP, because I think that my students who are more specialized for cybersecurity and hacking, they said, Professor, if you now connect your cell phone to mobile network in this restaurant, everybody can see what are you doing. I said, look, no problems, I'm doing normal things. I don't have some safety problems, but when it comes to electrical power system, we must be very careful, because I worked on projects in ABB about remote control of substations. What means that I could only, over internet, monitor what's happening, but I could not send the signal to disconnect circuit breaker. What means somebody can now disconnect circuit breaker and we are out of energy, somebody who is skillful. That's why our electrical power system, we are very, very conservative. And we have to be, because it's critical infrastructure, reliability aspects are at a very high level and so on. So that these are things which should be addressed. From one hand, we need data, we need communication infrastructure, and at the same time, we have also to think about policy, we have to think about regulation, and now this is what is on our agenda. Thank you very much, Professor Young, for comment and greetings to Chongqing.
Yeah, thanks. Thank you very much.
Yeah, thanks again. Yeah, cybersecurity is very important and touching everyday life of all of us, I think. Yeah.
Okay, can you hear me?
Yes, Professor Lee is our long-term collaborator. Thank you very much for joining us. So, please.
Thank you. I have some questions discuss with Professor Taria, and I'm very honored to attend the seminar, and the speech is very interesting for me. I have some questions. The first question is that Professor Taria, you know, different countries have the different development ways for the smart grid grid. You know, in China, the power company, such as the state grid company, for the power grid, installed many the PMU terminals in the 220 kV the voltage level, the power grid. And how about the PMU in Russia? And I know that from your speech, you mentioned the PMU and how to use the PMU to identify the dynamics of the power systems and to support the smart grid. I think maybe this is questions we should consider. And also, you mentioned that in China there are the hybrid AC, hybrid HVDC AC networks. And how about the power networks in Russia? Maybe there are different types. Could you introduce this? This is the first questions. And the second question that we know that you're very famous in the worldwide, and you are the editor-in-chief of the international journal. Could you give us some advice how to write the good paper, or how to increase the acceptance for the journal? The two questions. Okay.
Thank you very much, Professor Lee. We have 3 questions here. Each question could be a debate of minimum 15 minutes. Let me the first question was the level of development of smart grid in different countries.
Я думаю, что я покажу вам синхронный источник, который находится здесь.
That's okay. So the level of smart grid development. So I would say that in the entire world, we have now already quite advanced smart grid technology. When it comes to phasor measurement units, in Russia there is a PMU system, there is a network of phasor measurement units. I do not have a full information to which extent it is used, but I can say that in the entire world, the number of phasor measurement units installed in the system has significantly increased. But the question is, are they really used? Are they really connected to sensible applications? And I think that we are now at this stage of connecting them together and implementing them to different applications. For example, for advanced, what means improved power system monitoring, which can then help decision supporting tools. What means we operators are bringing decisions, or when it comes to fast processes in which operators are too slow, can we then have autonomous systems which will help system to be reliable, to be safe, and so on. The answer is yes, the smart grid technology has been increased also in Russia, naturally. In the entire world, the number of phasor measurement units in China is massive. Again, in conclusion to this part, it's important to which extent they are connected to sensible operating applications. The problem is that the system is very conservative and engineers are hesitant, they're unhappy to implement something advanced. I demonstrated smart frequency control from Britain. It was, I think, one of the very first demonstration projects in the world, and this application is still being tested and will be, I believe, in 5 years' time, 3 to 5 applied. I had previously approaches, I remember some 5 years ago, about protection of the whole system. When I went to talk to Alstom company in Paris, the answer was, Professor, it's too adventurous, it is too advanced. We have to wait for 10 years time to implement this approach. Well, the second, I know that the third question was about the situation of HVDC networks or hybrid HVDC and AC. I can say, and the question about Russia. Russia had, after the Second World War, 3 massive, huge HVDC transmission lines, what means Russia is one of pioneers in the world demonstrating capabilities of having HVDC. I don't know very well the whole Russian network, but I'd like to point out, yes, Russia already had demonstrated and showed to the world how HVDC can be used. HVDC is used in big countries where we have a so-called angular stability problem and a problem of transmission of energy over large distances. In the United States, for example, but also in China, there is a need for transfer of energy from Xinjiang province, which is in the western part of China, to Beijing area, for example. So yes, this is that what is now an ongoing process. And the second question was about phasor measurement units and their implementation. They are implemented traditionally at high voltage level, what means 200 kilovolt or 110 plus. But how about phasor measurement units in distribution networks? We have now also a need for this type of phasor measurement units, but this type of phasor measurement units must be more precise because we have shorter distances between substations, and then consequently there is a need for better accuracy. And we talk about so-called micro PMUs, micro phasor measurement units, which are also used. So I hope that I could cover some of your 3 bigger questions which you answer, Professor Lee.
Oh, thank you. Thank you.
My pleasure. Greetings to you.
Maybe, okay. Okay, we have another panel speaker from Hohai, yes, Hohai University Professor.
Hi, Professor Dennis.
Yeah, hi.
Okay, thanks for your invitation to participate in this seminar. Thanks, Professor Vladimir. Thanks for your wonderful speech. I'm from China, from Hohai University. I have one question. So I know you talk say about the data science. Maybe used some many methods such as the machine learning and deep learning. Could you tell us some future directions about the AI on our this huge data? You know, these days one tool is very popular, the Chat GPT. Could you tell us some more? Thank you.
Thank you very much for this question. Firstly, we have different types of problems in electrical power systems from monitoring, protection, control perspective, and in some cases the speed of classical applications is critical, and then we have a need to move towards data science-based approaches. In some cases in which the problem is highly non-linear, we also need alternative solutions. What means that, practically observed, these are situations in which we do not need data science, do not need artificial intelligence, machine learning. Everything is going well. But in some cases, for example, fault location in distribution networks, we need data science, we need artificial intelligence and machine learning. And in this context, in my opinion, firstly, data scientists cannot just come and say, okay, we have solutions for everything what you have. For us, everything is black box. So they can practically stop all companies working because they have all solutions, because everything is black box, training, that's it. But in my opinion, we need to understand the physical process, and there is a need of combining knowledge and efforts from those who understand physical process, in this case it is electrical power system, plus data scientists, so that they together can work and then create reliable solutions and flexible, and this is exactly that what I am doing right now with the team, in which I have data scientists from Skoltek and University of Belgrade, and from Shandong University I have those researchers who are understanding better electrical power system dynamics, plus my former postdoctoral research associate, my researcher who is now in India, who is a little bit coordinating everything that together. So joint efforts from research perspective. They use graph neural network. Please don't ask me what it is because I'm not specialized for this. And also thank you very much to previous presenters saying such a nice words about me. I consider myself as quite a normal faculty member trying to contribute to the society. As editor-in-chief, I maybe became more popular, probably because of my very gentle approach to all researchers, authors submitting papers. So, and that was the second question from the previous, question about how to write a paper. That's a separate topic. I have a presentation about this topic. I would be very happy to talk about that because it is the art of writing papers. How to write efficient paper. This is not easy, and I can give a comment that in some countries, children from age 5, 6 at schools learn how to present themselves. In some countries it is maybe not that important, but it is at the end of the day important. So data science is important. There is a need for combining efforts of specialists for the system in question, plus data scientists, and the solution is together. Thanks for this question, Professor
Okay, thanks
Sun.
for your answer.
Yes, and by the
In
way,
the future, welcome you and other professors to visit China and visit our universities.
yes, yeah.
Thank you.
Yes, yeah. By the way, my surname is Terzia. Terzia. And in China, they can say Vladimir, it goes Terzia, something like that. In German, it is Terzia, because Z is Z. And then it's like Professor Dennis said Terzia. Thank you.
Sorry for misspelling. Okay. The first name I spell, I think, correctly. Vladimir is easy. So I hope it's same as in Russian and Serbian and everywhere in the world. So other questions? Maybe we can have some, while our online panel participants are thinking about asking some questions, maybe we have some questions from audience. Okay.
Thank you for a very interesting presentation. And I would like to extend the question about data. On your picture about digital twin, when you show this picture, you said very useful thing that we need different models for different tasks. And because of this, for example, for state estimation with PMU data, we can use a linear model. For optimal control, for optimization on some future horizon, we need we can use just linear model. We need forecasting and a little bit different models and different model in this digital twin. But is it useful and is it possible to make some to develop some platform on which different models can work together and can exchange the data? So this is a question.
Thanks for this question. The answer is naturally yes, and in digital twin it could be possible to have, for example, model A, B, C. Model A is for one purpose, model B for second purpose, and so on. I would give one example. Voltage stability is a problem, as I talked about some processes which are very slowly degrading system, and the voltage stability has a so-called long-term voltage stability problem, like 15 minutes processes in which slow, gradually increased load is causing voltage drop, and when we reach one voltage level, then voltage can never return back. It's classical in theory of electrical power systems. For such processes, simplified models could be utilized. And for this process, maybe operation of on-load tap changers should be taken into account, but not something what I will mention in the next case. There is another type of problem which is linked to short-term voltage instability, which is now one of new problems related by integration of power electronics integrated generators, like type 4 wind farm. What means wind farm connected over power electronics, inverter. This inverter has high dynamics, and to assess a problem of short-term voltage stability, we need to have EMT level, electromagnetic transient processes level model, including fast transients related to power electronics. In other words, if we analyze any system can be described, dynamics can be described through its time constants. If we analyze one type of problem in which we say, okay, these are time constants, like 1 minute or 5 seconds, then it's one type of dynamics, and we have that level of development of the software. Or if it is fast transients, in our case, electromagnetic type of transients in which we are in a millisecond domain or even moving to a micro, then it should be another type. In this context, in advanced digital twin, we could have several options of the model. Each model is fed from the physical process by data appropriately, and consequently, then we could have applications at a different level. This is quite a nice comment, very practical, and of course, thank you very much for it. Do you mean platform in digital twin? Oh yes, now we are talking about, so what can we create a platform which can integrate a number of aspects? I would say yes, but the question is, do we need that? If we really need, then the answer would be yes, and let's use different type of communication protocols to integrate data from, for example, substations. We have one type of communication protocols, but if we have, for example, electrical power system of Germany and France, then we use so-called common information models, CIM model communication protocol. Then we use it if it is necessary for the purpose of integration of larger countries, a number of countries, and it would be possible. It's also the question of oversizing the problem and creating a giant, which is uncontrollable, and the balance and trade-off between aspects should be done. I know that you are working on practically oriented questions, what I experienced last August in your impressive laboratory. So thanks. I would say yes, but considering the application in question and the needs of that, what we want to create and build. Thank you.
Maybe I can add something just to say, to remind the words of Albert Einstein, that the model, mathematical model actually must be as simple as possible, but not simpler. So that's what you're talking about, I think. Yeah. Yes. So maybe other questions from online now, maybe? We can combine like an online and live questions. Anybody can ask, not only the invited panel speakers. So from online, people are still hesitate, so no problem about this. So maybe, oh, Ilya, okay, so you're, oh, Denis, okay, so you're all hidden, you should come closer, I really cannot see you.
So, dear professor, first of all, thank you for your such an interesting and even inspiring speech, because you pointed out not only some pure renewables and the questions about them, but also some classical things in electrical engineering like transient, stability, power system control and protection, and so on. I would like to ask even 2 questions, if you don't mind. We also study some issues in Russian power systems accompanied with false operation of relay protection and so on. And we have some problems with, for example, current transformer saturation and false tripping of differential protection, for example. And one of the ways of avoiding this problem is to replace some classical electromagnetic transformers, current transformers, with digital, and to implement some modern principles in relay protection. I would like to ask, what do you think about the replacing of relay protection implementation in from terminal base, like now, yeah, from different devices like terminals into server base, like computer base implementation? That was my first question.
Otherwise I will forget maybe. So excellent question. Thank you very much. It's a very specialized question related to power system protection. Today, modern power system protection devices are like computers, microprocessor based or multi-processor based. One processor is for data acquisition and conversion from AC to digital, phasors, and extraction of amplitude, phase, frequency. Another is for control, another is for communication. So maloperation of relays is something what can happen also as a consequence of processes which are happening at instrument transformers level. Instrument transformers are voltage transformer and current transformer. Voltage transformer is transferring 110 kilovolts to 5 volts. What is 110 volts as an input to relays. Actually, it's 110. Then another conversion to low level of signal. Current transformers are 2000 to 1 ampere, and so on. So, with current transformer, there is a process of saturation. Saturation means that analog signal at the primary side is not transferred one-to-one because there is saturation effect. So from one purely sinusoidal waveform, we receive something distorted. And then protection is obtaining wrong information from primary process. And for this purpose, to avoid the problem, we can use Rogowski coil-based instrument transformers. That's one of solutions. So I would say any new modern substation or digital substation very often is moving towards non-conventional instrument transformers. I didn't have time to talk about this slide in which I showed the data flow from bottom to the top. The left substation was classical and the right one was non-conventional, in which we had non-conventional instrument transformers, in which even information about voltages and currents is transferred to digital form, even at the transformer level. What means it's not the transformer is then sending information over cables to digital relay, in which we have a transfer in AD converter analog to digital. So that's something what is important, to get a realistic information from primary currents and voltage which are very high. And we cannot put this information to microprocessor-based device which explode instantaneously. For this purpose, non-conventional instrument transformers are welcome. And they can then support a number of efficient operation of power system protection. For example, to protect power system transformer. It's a very expensive element of the system. The most expensive is generator, then transformer, then transmission lines. But transmission lines are expensive because they are huge, long, and that's why they're expensive. So transformer is protected. Oh, I'm so sorry, the translator maybe is having problems too. I'm speaking so fast. It's about differential protection. And differential protection is very sensitive to instrument transformers, and that's why application of non-conventional instrument transformers is very welcome, to use approaches of so-called the second harmonic blockading of inrush current, and one of my PhD degree students is right now working on this topic. So I would just say that every modern digital substation is now actually bringing decision to use non-conventional instrument transformers, in which we will have more reliable operation of numerical devices. So you wanted to ask second question. I hope that I answered your question. Thank you very much. It's a very specialized question.
Thank you. And my second question could be shorter, I think. We also study some issues about power quality in electrical power systems, and this problem is really specific for our region, Irkutsk region, Krasnoyarsk, and so on. And what do you think, or maybe what is your, I don't know, experience about these problems, these issues of voltage distortion problems in general in the world? Is it an actual problem now, or maybe this problem is specific only for Russia, for Irkutsk, and so on? Thank you.
Thanks for this also very specialized question. I can say that I am specialist for power system protection, but also for power quality, but I cannot talk about that in front of this audience. It's too specialized. But power quality is a topic which has to do with the following. Firstly, you are buying any product, for example, this microphone. It must satisfy some quality requirements. At the same time, energy is also a product. We buy energy. It must also have some attributes defining its quality. So, from the perspective of power quality, we also expect that the delivered energy, actually delivered voltage, is purely sinusoidal waveform. If the company is having huge number of generators, this delivered voltage will always be a sinusoidal waveform. That is attribute of strong networks. We call it so-called infinite bus network. But this is not always the case, particularly with the case in which we have inverter or power electronics connected generators. These networks are everything but not strong network. They are very weak. And consequently, this waveform can be not sinusoidal, but something distorted with many harmonics. These harmonics are coming from customers. Because the network is not strong, this current taken from the different kind of processes is strange, and it is creating these distortions. So it's very interesting feedback phenomenon. And recently, it was last year in December, I delivered a lecture to Rossetti. It was 2 hours only talking about power quality. And interestingly, I remember when I asked the question, when I was a student in year 3, a professor who came from industry, he couldn't explain that so that I could understand. And I, believe me, understood this question when preparing this presentation. So it took time for me to understand, 40 years maybe. So that customers are creating this problem. So I would say, answering to your question, power quality is a problem in the whole world today, particularly in the countries in which we have more non-linear customers, arc furnaces. You have, I think, arc furnaces here for melting. Yes, so you have lots of customers which are very non-linear, and they are creating consequences on power quality. And what is now the problem? If we have higher harmonics, cables, transformers are, you know, they have aging processes. They are becoming older. So you buy a power system transformer and you expect that lifetime is 50 years. But with harmonics, it is aged faster, like working hard work, and then becoming older quicker. Although today do some exercise is good for us adults. But it's about aging processes on asset of the electrical power system. That's why power quality is an open problem, is important in every country. And the trend, as I see, is that power quality is becoming even more obvious problem, considering that the networks are becoming weaker. What means with integration of renewables, network is becoming weaker. And that's why we have a need to monitor the level of strength of the network. This is one of questions of Megagrant project in which we want to, and that's why we are monitoring H constant, system inertia monitoring fault level, to try to combine them together with harmonics. Interestingly, what was in my thoughts some 2 years ago with one of my PhD degree students, to combine them together and to create a formula which will express the level of system GIP cost, resilience. So that was something. What is interesting, I like your question, you're very specialized, and then it's easier to me to talk about that, but it's maybe not easy to follow for the broader audience, but because we spent many years to learn these aspects. But I want to point out, when it comes to harmonics, we have to extract them properly. We need digital signal processing. So that's one of comments. So thank you very much for this.
Thank you very much. Very nice conversation, always enjoying such. Yeah, okay, Professor Karamov have some questions. Dmitry, please.
Thanks a lot, Professor, for your presentation and very useful information. Installed capacities of renewable energy sources, photovoltaic systems, wind farms, biogas stations, and other. And I want to hear your opinion about current stage of storage devices development and integration of these storage devices into centralized energy systems.
Thank you very much for this very important question. At the beginning of my presentation, when I showed the electrical power system with the wind farms and so on, I said that storage is game-changing technology. What means, in other words, having storage elements and enough capacity of storage, we are in the position to cope with the problem which is called intermittency of renewable energy sources. Intermittency means we have wind, but we cannot have wind on demand whenever we want. We have wind or we don't. We can forecast wind. Similarly with sun, we can forecast, but we cannot be 100% sure that we will have it. Furthermore, we can also have disturbances in the system when we will suddenly have a huge outage of something, and then how to compensate this lost power. One of ways is very simple: to disconnect customer. Disconnect light under frequency load shedding, under voltage load shedding. What we have to do under certain conditions to retain system stability and to prevent power system blackout. But storage is one of key questions of storage: how to have an element with high density of energy. High density is important because in a small sized element you can have lots of energy. And that's one of problems. Another problem is charging and discharging. How quickly we can recharge this battery storage, and for how many times. And what is the optimal strategy of discharging? So that's a control problem. Then one of questions is, do we have sufficient lithium in the earth for all our needs? We can say storage is excellent thing. Lithium is even the best because the density of energy is huge. But the problem is, do we have enough lithium? That's why we have different other technologies like redox flow and so on. These are also problems which are related to feasibility of something. And in this context, I can say that Russian scientists, based on material science, are making huge progress. And also at Skoltech, I know that Professor Abakumov is doing a number of things, and the role of the power system group and also those who are dealing with electrical power systems is to optimally integrate storage components, which are of critical importance, but also in microgrids. For example, you have a place with gas platform somewhere where you have microgrid, but it's a small grid, not a large-scale grid, which is very often operating, or practically always operating autonomously, what means isolated from the larger power system. And then particularly this kind of microgrids storage is very important to help and support system operation without interruption, without blackouts, and in a stable way. That would be my answer to your question. My pleasure.
Thank you very much. It's a very important topic to design very advanced technologies and reliable for energy storage. Okay, so please.
Just I have only one small question. You speak about, firstly, thank you very much for your presentation. And firstly, you said about switchgear, AIS and GIS, and gas isolation switch and air isolation switch. And you said about SF6. SF6 gas is not ecological. It is not ecological, and now new, a lot of factory produce new devices with blue gas, isolation gas. Maybe you know this, but how you think about this? Yes. Azot. In Russian, голубой газ. Now I don't know it. It's blue gas. Translate. But what do you think about these switch gears when come in our country? Yeah, it is because it is technology go to our country.
We are talking about switchgear. What is switchgear in electrical power system? You know, electrical power system, we have generators. The voltage at output of generator is 15 kilovolt, for example, 15 to 20. You cannot put it too high because construction of generator would be very difficult. And then we have immediately switchgear, in which we have substation, in which we move from 15 kilovolt to 400 kilovolt, and we transmit energy, or we move to 700 and we transmit. So inside of this substation, we have switchgear, and the role of switchgear is to interrupt current. To interrupt current is not easy. It's equivalent problem to stop a big train. You know, you cannot instantaneously stop the train. It's inertial system. The system has inertia. And in switchgear, we have a circuit breaker as the heart of switchgear. We have also disconnectors, we have earthers, but in principle, circuit breaker is the key element. And now, we can make all these elements in so-called air, or in open space. We talk about air isolated. Air has its, it's an isolator. It has capabilities like an isolator. Of course, these isolation capabilities are good, but there is a problem if you want to have a substation in a house, for example. We do not have enough space. Then we want to reduce the space. We can do that. Instead of having air, we have sulfur hexafluoride, SF6. Then I remember I was in ABB at that time in 2000. Angela Merkel was asked, sorry, this SF6 is going into the air and is negatively affecting atmosphere. When you add all SF6 substations, it looks that it is a problem for the society. And then there was the question, you know, so I was thinking, so will they shut down our factory? But there is a need for switchgear which is smaller. You need switchgear in a ship, so in aircraft carriers. You have this kind of SF6, and ABB delivered also extra, very special switchgear for military purposes, I remember, and for other ships, for example, industry. And then came another option of using other gases instead of SF6. So one is it azot N? Is it N? And 2, but I can say that these are also other gases which have complex name. It's a chemical name, I don't know very specifically, but I can say these are other gases which have good isolator capabilities. And there is one more thing, that what is happening in substations are sometimes it's electrical arc. Honestly, this is one of my favorite topics in the past, which I worked on mathematical modeling of electrical arc, long arc in free air, long 5 meters. It's very impressive phenomenon with elongation effects. It's plasma. I'm not plasma physics. My view was macroscopic view to everything. And if arc happens, then the question how quickly isolation capabilities will be recovered in SF6 or air or N and so on, this kind of environment. So these are different aspects about the question when it will be changed. You know, there is a lobby of industry. You know, I was very happy when ABB said, no, we are fine. Our company will still keep on manufacturing SF6 because the reality is that there is a need for SF6-based top products. You have also SF6 circuit breakers, SF6 substations. You know, you cannot just say, oh, look, ecological, it's not good, let's destroy that. Unfortunately, critical infrastructure is different. It's not like Bill Gates changing his operating system, Windows 1, 2, 3, 10. Now I don't know which is the number. I don't care about that. But you cannot change 50 hertz to 60 hertz. Although we can ask ourselves, why in USA they have 60 hertz, we have 50? Even in Japan, they have one island which is 50, one is 60, the rest is 50, because they got generators from USA, and it was 60, and then between them there is cycloconverter connecting them, and so that's quite interesting. So we should also accept the reality when it comes to changes of technology, you know, because it's massive investments into move from one types of isolators. On the other hand, when it comes to big, densely populated cities, SF6 and these kind of technologies are definitely good. But when it comes to Russia, open space, you have lots of space, you have no concerns. Look, Siberia, it's really, I remember I used to fly from, when flying to China, I fly over Russia, and that was always impressive to look at these huge rivers, and that was fantastic scenes, or forests which you have, so you have enough space. But, or look, for example, you have a big tall building, skyscraper, you have SF6 substation, so how can you change this? It's not that easy, you know, action. So it will come with time. And I cannot now say, is it, you know, you have lobbies. They say, look, SF6 is dangerous, we will die, all of us. So why? Because they want a new investment and they have business case. So we should just also assess these, who has benefits, but we are engineers just to talk about reality. Yes, probably SF6 is not good to breathe it every day, but well, a recommendation to immediately change all SF6 substations in the world would be nonsense from engineering perspective. Thanks for this question.
Maybe I can say something like on behalf of the Russian Academy of Science and the society. Like I think the managers and lobby and politics is very important, but I think we are scientists also should have our word and the influence on this, because we know sometimes a little bit more comparing to the ordinary. Yeah, this is on the picture. There was a small government, so yeah, it's a good question. So other questions? If okay, yes, please.
Vladimir, you know my English very, very bad. I am sorry. You are a wonderful speaker. Thank you. I would like you one questions. Organic fuel plays an important role in energy sector in our country. Is it possible to switch on economic without carbon in Russia? What do you think?
Thank you, Professor Ekaterina. It is a question which is, yes, is it possible that we move to carbon neutral society using different approaches by minimizing CO2 emission, in which fuels mentioned can provide its contribution? My opinion is yes, this is definitely possible. The question has also to do with the investments, of course, that ecologically observed, it will be wonderful to achieve that CO2 neutral society. And on the other hand, we should respect investments into technology and utilization of this technology. At the same time, I'd like to point out that the different societies have a different level of problems. Russia is a huge society, huge country with lots of forests which are helping in this CO2 neutrality, but I'm not that specialized for this kind of problems. I can only say something what I was thinking about, eventually read in some books or discussed with several colleagues. But I'd like to point out that different countries have a different nature, different generator mix, I mean different portfolio. We could see Russia, coal, gas, water, oil and renewables. And in Denmark or in Britain on this night, 50% of renewables. I think, for example, it's impossible in France. They have 70% of nuclear power plants, so that in their case it is complicated. So it's from country to country. It is our intention to reach CO2 neutrality, and organic biofuels can definitely contribute for this. So thanks for this question.
Ecological impact is very important. It's our health and health of our children and next generation. So we have some questions from the chat. Let me read this question. What the problems in the network with the isolated neutral for the definition of the damage that's of the connection? That's a question from Sergei Tiguntsev. Yeah.
This is exceptionally specialized question. Exceptionally specialized question. What means we have electrical power system in which we have three phases. Phase A, B, C. What does it mean? Again, it's you should study electrical power systems. And electrical power transformer having these three phases has a neutral point which could be connected to the ground. If we connect it to the ground, particularly in medium voltage networks, or then it has to do with different aspects, with safety of equipment, with safety of people, and also with protection of the system. If we have it connected to the ground, we enjoy if a short circuit happen in a system, that's what we are talking about, short circuits, and then we have a huge short circuit current. And power system protection loves it very much. What means there is a normal state and there is a faulty state, and we know what is the difference, huge current and no current. However, in systems without efficiently grounded neutral point of three-phase power system transformers, we do not have that high current, and then we have difficulties to create efficient protection principles for this purpose. We talk about capacitive currents which do exist, and then we have to have very sensitive, very precise power system protection. I mean, firstly, instrument transformers must be very precise, and also protection principle has to be precise. Firstly, overcurrent protection, and then we follow to directional overcurrent protection. We also utilize distant protection, which again we have then problems with the fact that the currents are very small. So I will actually not exclude the distant protection from this conversation. And the treatment of neutral point can go also into a hybrid solution in which we use so-called Petersen coil that's a technology used in Germany and used to be used in Germany, and in Russia I think that both options are used. If you now ask me a question which one is better, and so to have efficiently grounded, number one, two, with Petersen coil, number two, three, and number three, not grounded, which is from safety perspective a bit more complicated, I would not feel free now to give a direct answer. I only can say we could make a study for the networking question. At the end of the day, we must satisfy standards and recommendations from Rossetti, and it should be in line of that. It's a big question, very specialized question, and I'd like also if you could also join and maybe give your opinion, if you unmute yourself and give your comment, if possible.
Да, Степан Георгиевич, если есть возможность. Yeah, if you available, of course, yeah. Степан Георгиевич, I hope you satisfied with your question. Все, думаю, вполне развернуто. Okay. So, yeah. So before you are thinking, maybe we have a short interruption, and I would ask all the participants to switch on cameras and to take the picture of everybody who is online. Yes. As kind of proof that the event was happened. Also, I know that our Chinese collaborators always asking me to do these things, so I decided why not to do this. So also Russian, так, если есть возможности, то, пожалуйста, включите камеры. Вот Алексей Жуков is my PhD student, now moving to UK, I think, here, to Ireland, actually. Если, то может, пожалуйста, включите камеры, сделаем фотографию. Может быть, можно, да, сделать фото кто-нибудь экрана? Фото экрана, да, это можно сделать вам. Да. Ну, там есть принтскрин, как это, да, принтскрин, конечно. Yeah, print screen, that would be fine. Yeah, and to the end of the meeting, I would ask also not to leave, and so we will take the photograph of the participants. That would be very nice. Пожалуйста, не уходите после доклада, мы сделаем коллективную фотографию. Это будет тоже важно. Yeah, I should look to this. Yeah.
I'm looking at camera, then I look at them in their eyes.
Yeah. Yes, exactly.
Now we should know if it has been done or we should start behaving normally.
Когда сфотографируете, пожалуйста, скажите. все получилось, да? Okay, ну, спасибо большое. Thank you very much. So, yeah, yeah, it's done. So, other questions, if or online also maybe. Thank you very much for. Also. Yes. So please.
One of questions, which is really very interesting question, it's about publications. And I feel also this opportunity to say a few words. It's very important to firstly conduct very serious research, answering serious questions when it comes to PhD degree. That means that this kind of research questions should result in new knowledge, something what is new. And if it is new, then we also want to know it is really new. Can we get a recognition from the world audience that it is new? We do that by submitting our results to journals to publish our results. And when we publish, then it is protected from forgetfulness. It will not be forgotten. It will, on contrary, contribute to future generations. And the role of journals is to protect knowledge. And it is a quite exciting and important work, important for younger generations which will read knowledge, read papers, and then give their own contribution. To write an effective paper, it is a skill, it is art. You should think how to formulate title, abstract, body of the paper, how to define the problem. We have to define problem, what is the problem statement, what are problem challenges, what are existing solutions, and what is a new proposed solution, and how to compare it with the existing solutions in the context of the defined problem. I also know experienced writers of papers already write the paper in the way that they write it for reviewers. They think what reviewers will ask. So if you expect that reviewer will ask some strange questions, you say, and the research is focused on this, this, and this, and we exclude this type of problems. And then reviewer, if he's complaining, sorry, I already said this, that's it. So it's a strategy how to write a paper. And you can create your own strategy by reading other papers, but particularly writing papers and starting fighting or communicating with reviewers. Sometimes reviewers are arrogant, they're not fair, they expect to, and that's why as editor-in-chief I'm here to help authors and reviewers to balance that. These are crazy reviewers, crazy authors, maybe crazy editor-in-chief. That's the worst case. But based on my experience, people told to me, if you become editor-in-chief, you will have so many enemies. Honestly, I got so many friends. I'm trying to be fair, always encourage those who have rejected paper, because I also had rejected papers, minimum 20–30% rejected papers. But today we have to understand, rejected paper, it doesn't mean that this paper is totally bad. On contrary, this paper can be further improved. It's a starting point for a new step, and you never give up, and then finally you realize that I have almost 500 papers published. If each paper has 10 pages, you can imagine how many pages. Of course, not all of these papers has its value. It's so new knowledge, it's a demonstration of a work. And also when you have a large team of students, 10 PhD degree students, you have minimum 10 journal papers on a year. If it is more effective, then it is 20. But it is important to know how to formally present your results, and also how to diplomatically communicate with the journal to make sure that the paper, that the knowledge has been recognized, accepted, and after that you can move forward and work on other research questions. So that's about publications, and I would like to encourage all of you to work hard and also to read the best possible journals, and then also to try to provide your own contribution. Sometimes language is a barrier, this is true, but you try to learn, in this case, English language is now a common language, but I can also tell you that slowly some top papers are published in Chinese, so that I use my students sometimes, please translate it, but we have also good translators. I'm particularly good at using Yandex Translator because I'm translating Russian to English, Russian to Serbian when I have a need, what works quite well. So that's my comment about journals, and I'm trying to inspire all of you to write. And if it is about electrical power systems, feel free to contact me. I'm always very happy to help and support, to provide my encouragement, so that that's also my duty. Dennis, for you.
Thank you very much. Okay, I think we are eventually approaching to the end of our great, I think, meeting, seminar, IPolytech Seminar. And I would like to thank Professor Vladimir to giving this excellent talk, and also for this communication for all the participants who contributed to this. So we took almost more than 1 hour of actually communication after this talk itself, so it was taking more time than talk itself. I think it's excellent. If you have some questions, I think you can, there was an email, so you can drop, I think, email to Professor Vladimir, and he will be very happy, and myself also. You can ask and contact us. And okay, thanks again, Professor. Yes, and now I invite everybody, I think, to the stand to take the picture for all of us.